Our second example of partial fraction decomposition is going to be mostly the same as the last, although there's going to be one main difference that we have to be aware of as we're going through the process. So we're going to be looking at decomposing fractions with repeated linear factors. Now, what it means to have a repeated linear factor is something like you see down here with this starting example. You notice we have x minus 2 to the third power. Now, if I were to try to do this problem exactly the same as last time, what would end up happening is I would think, okay, well, maybe I'm going to split this into three fractions. The first one, since it's an x minus 2, that must have x minus 2. And then the second one's another x minus 2, so that must have x minus 2 on the bottom. And then we have a third x minus 2. And then we just have, well, I add them together, so it's an A, a B, and a C. And that's a problem just because then we're not really splitting up this fraction. All these denominators are the same, and we could just add them all together and say A plus B plus C over x minus 2. And that's really just a single number, and so it would kind of render our method just not very effective. So this is not what we're going to do with it. The main thing that's different about this is we're going to now have a fraction for each power of the repeat. So what you'll notice here is we've got x minus 2. The second one's x minus 2 squared. Third one's x minus 2 to the third. We just work our way up until we hit that top value, until we hit that degree on the denominator. So that's going to be our main difference, is that we just need to keep working our way up with this one. I've got an example for you that we will work through, and here it is. So this example, we want to, first of all, like the last time, factor the denominator as much as possible. So we're going to factor this one. We have x to the third plus 4x squared, and we can take an x squared out of that. So that's x squared, and that's x plus 4. So with this factorization, we're going to set up, in this case, three to be precise, 3 fractions, and make a system to solve and find A, B, and C like we've done before. Here's how that's going to work. Now we can, again, start in any order that you want. I'm just going to pick off the easy one first. I'm going to do the x plus 4 because it's not repeated. So I'll do x plus 4 as one of my fractions. We'll do A over that. So that takes care of this one. Now here are the repeated linear factors. We've got x. So it's going to be one of them as x and another one as x squared. We have to represent each power of the repeat. And so if I know that, then I just put a single constant over each one. You just work your way up the alphabet. You can have as many as you need. The book may have them labeled a little bit differently, but the labels don't matter so much as the numbers that actually come in at the final answer here. So this is going to be my equation, and now what I'm going to do is, like before, in that last example, I tried to get rid of all the denominators, and so I'm just going to multiply by everything in the denominator, which is x squared times x plus 4. That's going to get rid of all the denominators somehow. So here's what that's going to look like. In the left-hand side, it's going to get rid of everything, and so we're going to be left with 5x squared plus 7x minus 4 on that side. Over here, we get rid of x plus 4, so that makes x squared left, so that's going to be a x squared. In this second term, x gets eliminated. What's left over is x times x plus 4, so that's going to be b times x plus 4. And then finally here, the x squared gets canceled out, so we're just going to have left c times x plus 4. All right, now that we have it all laid out without fractions, we can go ahead and isolate things, try to get the same types of terms that we have on the left side as the right side. We've got ax squared, we're just going to leave that, there's nothing to distribute. But then here we've got, if we distribute the bx, that'll make bx squared plus 4bx. And then with the c, we'll have plus cx plus 4c. And like last time, we're going to group like terms together. We've got ax squared and bx squared. I'm just going to go ahead and factor out the x squared right away. So what that means is that it's going to be a plus b x squared. I'm just combining those like terms. I've got the x terms over here. That's going to be next. I'm going to factor out the x right away to have 4b plus c x. And then the last one, 4c, is all by itself. So that one is just plus 4c. Now that I have that, I can line up the pieces on the left and the right that match up with each other. So I've got an x squared term. I've got 5, and I've got a plus b. That's going to be one of my equations in the system. So I'll do a plus b equals 5. Okay, so that's my first one. My second one is going to be the x terms, and so there's 7x, there's 4b plus cx, so I can just do 4b plus c equals 7, and that's going to be my second equation. My third equation, final equation here, is we've got negative 4 and 4c, so that means 4c is equal to negative 4, and that completes my system of equations for this one. Now that I have the system set up, I can solve it, and you might notice that this one is pretty convenient. We don't actually have to go through all the row operations or anything like that because we have 4c equal to 4. So right off the bat, we know that c is equal to negative 1. So that's kind of a nice thing to get. Then we can do some back substitution. It appears that this one right here, we could plug in the negative 1 for c, and we get 4b equals 8. So then b is equal to 2. Finally, almost done here, but finally we have this top equation now. We have a b value, so we can do a plus b equals 5. Well, that means that, so we've got a plus 2 equals 5, therefore a is going to be equal to 3. So the actual solving part was not too bad at all. We have a, b, and c as those coefficients. Now, the final thing to do here is to summarize what this one was all about, and that is splitting it up into these fractions. So we had this as our original. We wanted to split this up into 3 fractions. We started with a over x plus 4. So this is equal to 3 over x plus 4 plus 2 over x plus negative 1 over x squared. If you wanted to just do minus 1 over x squared, that would be fine too. But now this original fraction, this complicated fraction, we've split up into 3 simpler fractions, and this is going to be helpful to you if you're moving on to calc next year. This will be helpful to you in certain situations to just lighten the load on problems that involve integration, which you'll find out about later.